Welcome once again to yet another lesson about capacitors. In our previous lesson, we were convinced that the capacitance is equal to A epsilon out of D. That was the capacitance of parallel plate capacitor. We proved that. But as scientists, we still don't just go and do things. We still have to confirm. We could have done it mathematically, but is it in the real sense? This is why it actually takes like a longer time if the vaccines are being manufactured and produced to be accepted. It takes time for people, especially the scientists, to accept it. People who actually are not in the science group, they can easily say, oh, the scientists have brought a certain medicine, whatever, or vaccine or whatever. But those ones in the science, they'll be like, first wait. Let us first do one more practical and confirm. Will it be effective? Then they do all that, and then they can finally say, oh, the vaccine is allowed. And that's why we have organization like the World Health Organization. It has to first confirm that a certain medicine, a certain vaccine, or a certain drug is acceptable because it has been proved. Even when you're in Uganda, we have even the standards that we have to follow. So you don't just wake up and say, I met an angel from God and told me to do this and I did it and it worked. My friend, you may be put in prison. So we move slow, but sure. So therefore, we saw this, but we want to be so sure that it is true. And therefore, for us to do so, we have to do an experiment. And that's why we have actually experiments to verify that this capacitance is actually proportional to A epsilon and inversely proportional to D. It is not one experiment. We are going to do actually 3 experiments, but in one, because we have to keep varying some and keeping others constant. And we are going to have to experiment. The kind of apparatus that we are using is differing. So the one we are using for this lesson is using a battery and a GLE. Now you can see our battery is there, our GLE is here. And then you can see these are the capacitor plates, just like we have them. These are the capacitor plates. They are at a separation of distance D. This is maybe X, this is Y, as you can see from there. So they are at a distance X, at a distance D rather. They are at a distance D from each other, okay? And then the area of overlap is A. And then there is air between them. There is nothing. There is air, right? I've not had anything. So therefore, what do we observe on the GLE? On the cordless electroscope, we shall only be observing the diffraction. So therefore, we shall keep 2 constant and vary 1. So the first one, we want to show that capacitance is proportional to the area between the plates, the area of overlap. So what do we do? This is the representation of our capacitor. This is the area. So we are going to keep the D constant and we keep this thing in air. So we are not changing the permittivity, we are not changing the distance of separation. We are only changing the area in contact. So how do we change the area? You can make it slide over each other. For instance, I can have this one rotate like this. Okay? So you see that some of the area is outside and some is outside here. So by doing so, I'm reducing the area. And you can see that totally there is no area of overlap between this capacitor plate and this capacitor plate. And I believe we do not have any charge. Okay? So therefore, what do we do? This is the maximum area. With the D kept constant and air between the capacitor plates, I reduce the area of overlap. As you reduce, you notice what happens on the GLE. When the area of overlap is reduced, you will actually observe that also the diffraction will have reduced. when the area of overlap is reduced, maybe I push this one this side, and this one bends, so the theta here will reduce. And that one shows that the capacitance is proportional to area. And of course, when you increase the area, this one increases. Okay? So that means if you want some good capacitance, you must make sure the area of overlap is as big as possible. Okay? You can see that one is done. We are remaining with 2. I said we are doing a practical, but we are doing 3 in 1. So now we want to see sure that capacitance is inversely proportional to D. That when you increase D, capacitance reduces. So therefore, we shall keep the area constant and we keep this capacitor plates in air. So what do? You can increase the D. Yes, I have increased the distance by moving this capacitor plate far away. Okay. What happens when you increase the D? You'll find that the area, that the diffraction is reducing. And when you reduce the D, maybe up that level, you'll find that, you are getting a high diffraction by the GLA. What does that one mean? That means that as you increase the distance, capacitance reduces, and as you reduce capacitance, capacitance increases. Therefore, capacitance is inversely proportional to T. Yeah, as if that one is not enough. That we need even to show that actually that the capacitance is proportional to epsilon. So what do? We still have the same setup, by the way. We are using the same setup. So this is the setup. We have the D. We are not going to change it throughout the experiment, and we have the area of overlap. If it is there, it is there. So we don't change in it. So the only thing we are going to do is that we are going to insert a dielectric. So when you insert here a dielectric, then you record the diffraction on the GLA. You call it maybe theta 1. Okay, theta 2. When there is this, you call it theta 2. Then when it is not there, you also record the diffraction because it is still working. And you record that one, theta 1. When there is air, theta 1. When there is a dielectric, theta 2. Okay? And you will realize that when there is a dielectric, the diffraction is bigger than when there is air. What does that one mean? That means that capacitance is proportional to what? Epsilon. Therefore, by getting convinced, there we become better scientists. Okay? I know it's better that you can take a note of something. Just a minute and then do so. So therefore, that is our setup. And I think I should remove this. Yeah. So this is our setup. That's what you're supposed to begin with. You can always pause the video and first record something. And I want to begin. Why do we even say that theta? Then we are talking about capacitance. You are looking at the diffraction. Why? Because we know that charge is CV. This is a direct supply. DC, therefore, the voltage is constant. Therefore, the capacitance is proportional to charge. Okay? But then we are talking about the diffraction, the angle of diffraction. Yes, the charge that will be on plate Y is the one that will bring the diffraction. So when there is more charge, there is more diffraction. Okay? Meaning that charge is proportional to theta. Meaning the capacitance will also be proportional to theta. That is the angle of diffraction. That's where we are beginning from. Okay? You can take note. Magnitude of charge stored on either capacitor plate, Q equals CV. And since V is constant, therefore, Q is proportional to C. Okay? Therefore, Q is proportional to C. And since the diffraction of the GLE is proportional to the charge stored by Y, and since the diffraction of the GLE is proportional to the charge stored by Y, therefore, this and then this. So we can begin now our experiment. So you are now convinced that when the diffraction is bigger, that means bigger capacitance. Okay? So now we shall have experiment 1. To show that capacitance is proportional to A, we are beginning with that. To show that capacitance is proportional to A. That's the common area of the capacitor plates, the area between the capacitor plates. Air is kept between the capacitor plates. Air is kept between the capacitor plates, and the separation D. And the separation D is kept constant throughout the experiment. And the separation D is kept constant throughout the experiment. When the common area of the plates is kept on being reduced, when the common area of the plates is kept on being reduced by sliding the capacitor plates over each other, the diffraction theta of the GLE keeps on reducing. The diffraction keeps on reducing, which shows that the capacitance is reducing. Which shows that the capacitance is reducing. When A is increased, that's the area. When the area A is increased, still by doing the same but in the opposite direction, the diffraction increases, which shows that the capacitance is increasing. The diffraction increases, which shows that the capacitance is increasing. This verifies that capacitance is proportional to A. This verifies that capacitance is proportional to A. Experiment to verify that capacitance is inversely proportional to D. Experiment to verify that capacitance is inversely proportional to D. So what do we make constant? The area and the permittivity. Okay? Yes. Air is kept between the capacitor plates, and the common area A is not changed throughout the experiment. Air is kept between the capacitor plates, and the common area A is not changed throughout the experiment. It is observed that when the separation D keeps on being increased, it is observed that when the separation D is increased, the diffraction theta reduces, which shows that the capacitance has reduced. Which shows that the capacitance has reduced. Full stop. When the separation D is reduced, when the separation D is reduced, the diffraction of the GLE theta increases, which shows that capacitance increases with reduction in the distance. This verifies that capacitance is inversely proportional to D. You can write that. This verifies that the capacitance is inversely proportional to the separation of the plates. That is D. Experiment number 3, to show that capacitance is proportional to epsilon. To show that the capacitance is proportional to epsilon. So we are keeping now the distance and the area constant. Okay? Yes, you can write. The common area A between the plates and the separation D are kept constant throughout the experiment. The common area A and the separation D are kept constant throughout the experiment. Full stop. New line. With the air between the capacitor plates, with the air between the capacitor plates, a diffraction the diffraction of the GRE theta 1 is noted. The diffraction of the GRE theta 1 is noted. So, you write a dielectric. A dielectric is inserted between the capacitor plates. A dielectric is inserted between the capacitor plates, and the diffraction of the GRE theta 2 is noted. And the diffraction of the GRE theta 2 is noted. It is observed that theta 2 is greater than theta 1. It is observed that theta 2 is greater than theta 1, which shows that the capacitance is higher when a dielectric is between the capacitor plates, which shows that the capacitance is higher when the dielectric is between the capacitor plates than when there is air or vacuum. The three experiments verify that capacitance is proportional to A is proportional to epsilon and inversely proportional to D. The three experiments verify that capacitance is proportional to that. You can be asked to describe one experiment, okay? You can be asked to describe an experiment to show that capacitance is inversely proportional to the separation of the plates. So you don't need to do all the three. Just you choose the same diagram, of course, you name it very well, and then you just do only for that particular part. For those ones who are interested in marks, okay, and I know majority of you are interested in marks. When I teach something new, students write that, teacher, excuse me, how do the questions come about that? Still, that is not the scientific reasoning. The scientific reasoning would be, how do we solve problems in society, even if we don't get marks? Because when you solve problems, then you are now a scientist. But then I know what you passed through. It is okay. So that's why I'm also telling you, when it is required to describe experiment, show that capacitance is inversely proportional to the separation of the plates, just draw this, then you give only that description about the separation of the plates. You don't now give us these other ones. Okay? We are moving on where? We are back. BSc. We are back. We are back. BSc. This is B. I like doing it like that. B. BSc. Back Science Education Consultants. Please feel free to follow us on YouTube. Always keep watching our videos, and you encourage others to watch them so that they can benefit. So that a video that we record with all these resources can at least help many people, then we can also be happy. Okay? We can also be happy if so happens. So thank you very much for always watching these videos and learning with us. Please subscribe, like, share, and encourage friends to be part of us. Next, we shall still do the same experiment. You know, we have used only one, so we shall do the same experiment but using other piece of arrangement, other kind of arrangement of apparatus. So be waiting for the next video. It is coming. Just click there and put always when we put you will be notified that we have uploaded a new video. Thank you very much for studying. Thank you very much for attending this lesson. Teacher course of Back Science Education Consultants.